All right, our momentum equation is written out there. That's the momentum equation for a flow in a boundary layer. And so let's see. Actually, before we get into this, we need to, it's going to help us to rewrite this in a way that when we first went through, remember, I don't know, 4 or 5 lectures ago, we went through and did the control volume analysis, and we ended up with something that kind of looked like this, but we had to do some mathematical tricks to get it to this point. And I just said, go look at the book. What we're going to do is reverse that step so we get something that looks more like the control volume version that we derived, because it's easier to work with for our purposes here. So let's do that. What we're going to do is we're going to make the observation that du dx plus dv dy is equal to 0. That's continuity, right? That's our definition of continuity. Why is that helpful? Well, I can add that to, let's say, one side of the equation, and it doesn't change the equation because it's 0, right? So I'm adding something that's equal to 0. I could, anything I want, I could add equals 0. I can add it to one side. It doesn't change the equation, but algebraically, it makes our lives a little easier. So we'll do that. So we end up rewriting this as follows, which is rho times the quantity du dt plus u du dx plus v du dy plus this thing we're adding in, which is going to be, let's actually multiply that by rho and u as well. So we're taking rho times u times du dx plus dv dy, right? That this thing here, just as a note, this thing here is equal to 0. So I can add it in without changing the equation. And then on the right-hand side, we just have what was left originally, which is minus dp infinity dx plus mu d squared u dy squared. Okay, so that's all we did there is just add in that term there, and then we're going to kind of take steps to reverse back to what we originally had. So let's see, if we do that, we end up with, see, I'm going to divide everything through by rho. So rho over rho, this rho. So this becomes 1 over rho on the right-hand side here, minus 1 over rho dp infinity dx, and then mu over rho. And actually this here becomes nu, right? The kinematic viscosity. Okay, so divide through by rho, and then where are we? Let's rewrite this. So we now have on this left-hand side, we have du dt plus what we bring together the two u du dx's. So that's 2 u du dx. And then we have, let's see, a v du dy plus a u dv dy. And that's equal to minus 1 over rho dp infinity dx plus nu times d squared u dy squared. All right, so then we can note a couple things. One, this here, right, this term here is actually du squared dx, right? If you kind of evaluate that out, it's the same thing, du squared dx. And then this term here is actually du times v dy through the chain rule. Right. Hopefully you can see that both of those things are true. So now we can rewrite this as something that's more useful for us, which is du dt plus du squared dx plus du times v dy is equal to minus 1 over rho dp infinity dx plus nu d squared u dy squared. Okay, just prep work for what we're actually going to do. All right, so now we need to take this equation and we need to substitute, which I wrote here, I guess. I like writing things and then having them on the next slide. Okay, so that's what I just wrote, hopefully. So now we're going to take our definitions of the average values and then substitute it in. So we said what u is equal, or u x y t, that's equal to u bar plus u prime. V is equal to V bar plus V prime. So let's substitute those in every time we see them in that equation. And if you do that, we end up with the following. We end up with, let's see, we have the derivative of U bar plus U prime with respect to time, right? Substitute U in there. And then we have the derivative of, let's see, U bar plus U prime squared with respect to X. Here we have, let's see, duv, so that's going to be d u bar plus u prime times v bar plus v prime with respect to y. And then on the right-hand side, everything else, well, it's almost everything else. So 1 over rho dp infinity dx plus nu times d squared u bar plus u prime dy squared. Okay, so that's what we end up with, I think, after substituting everything in. Just move this over a little. We follow that. Lots of writing. Okay, so then again, we need to get rid of our u prime or try to get rid of it. And how do we do that? We can integrate the whole equation over our time interval. So let's take this whole thing. Let's integrate this with respect to time from 0 to t int. All right. And now we have a big, long, tedious thing to do here, but this is where it kind of starts getting interesting because there's some things that come out of this that actually don't go to 0. Okay. So let's walk through, let's break out this, this integral. So what I'm going to do is let's write it all out where we break out everything into individual terms and let's kind of see how it plays out. So I'll try to conserve space here. Oh, sorry, this integral should be divided by t int as well, right? 1 over t int in front of that integral. Okay, so let's write this out. It becomes 1 over t int times the integral. So now this is this full integral of, let's see, the first term becomes du bar dt, and that du prime dt. And then we have, let's see, we have a du squared dx. We have a d, see, we end up with, so you factor that out with that quadratic term. In that second one, we get a 2 u prime, or u bar, sorry, u bar u prime. This is u bar over here. So just what I did here, d u bar squared dx plus d 2 u bar u prime with respect to x. And then let's see, what's the next one? We end up with d u prime squared dx. And then we have, let's see, d u bar v bar dy. We have d u bar v prime dy. We have d u prime v bar dy. And then we have d u prime v prime dy. And all of that is equal to, on the right-hand side, let's see, it's going to be 1 over t int. So we'll integrate the right-hand side too, 0 to t int of, let's see, minus 1 over rho dp infinity dx plus v d squared u bar dy squared plus v d squared u prime dy squared with respect to time. let's see, did I get all that? Oh, got to get over here. So this with respect to time as well. Okay. Yeah.
Are those V's on the right hand side? Are those new or is that?
Good. Yeah, I need to be more careful. So let's see, we have, you're right, it's new, isn't it? Not V. Yeah, thank you. So this would be on the right-hand side, new, right? Because it's, yeah, when it compresses the font, it looks a lot like V. So like that. Okay. So we should have V's on the left-hand side. We should have kinematic viscosity on the right-hand side here. Okay, so now we need to go through and decide, okay, which of these terms, when we take the integral, is going to become just the average value, which of these is going to become zero, and which of them is going to do something else. So we can kind of march through this and we'll start to see patterns. So first of all, let's try to pick out the terms that are going to be, when you take the integral, divide by the time interval, it's just going to go to the average value. Right, starting with du dt. Right, this one clearly, we take the integral of that, average value is not changing. That gradient therefore is not changing. And so you take the integral and it just becomes the integral back. So we'll put a little red box around the ones where that's true. Let's see, what about this second term? Well, du prime dt, that's variability around zero. So we integrate that, that should go away. So that one goes away. What about du squared? Well, du squared, right? It's u bar squared. So u bar squared isn't changing because u bar isn't changing. So that's just going to go to the same value that it started with. What about u bar times u prime? So 2 times u bar times u prime. Okay, so we have u bar, right? That's constant. You have u prime that's varying around zero. So we integrate that. A constant times something that's varying about zero should go away. Right? So this one goes away too. Okay, progress. We're starting to make it through this. Now we run into a complication here. Okay, du prime squared dx. So think about what is happening here. So if we draw this out a little bit, right? If I draw my velocity variation, right, this being zero and this is, let's say, u. If I draw my velocity variation as a function of time, like this, what happens if I take that velocity squared? It's always going to be positive, right? It now no longer is symmetric about zero. It's some number, right? It's a non-zero number. So this becomes something that we have to think about a little bit more. Okay. So I guess circle means let's think about it. Okay, continuing on, we have now du bar, v bar, dy. So two constants, that's just going to go to the constant value. Du bar v prime, dy is going to go to zero for the same reason. The other thing, the other similar one went to zero. Let's see, du prime. This one also goes to zero. Hopefully you can see that. And then this last term here. So now we have du prime, v prime, dy. So what happens when we integrate that one? We have something oscillating around zero. We have, which is u prime. We have another thing that's oscillating around zero. So do you think that if we integrate that, that's going to go to zero? I see a head shake no. What, do you know why?
There's a chance that both of them go negatives.
Yes, exactly, right? So if they're correlated, right? If they're purely random, like totally uncorrelated randomness, then it would be zero. But if they both go together at the same time, and one sort of causes the other, that means they're correlated, then that integral is not going to be zero. And let's think about this. So draw down here. So if we draw our boundary layer, this is, yeah, let's say like this, right? So you have this boundary layer like this. If we had a little bit of fluid, let's say right here, let me draw it in red, have a little bit of fluid right here, and it suddenly moves in the vertical direction, right? It's coming in at this velocity and it moves in the vertical direction. It fluctuates vertically. What's going to happen to the u velocity in the adjacent fluid when that happens? It's going to slow down, right? Because you're moving something slower vertically into a faster flow stream, and it causes it to slow down. So those are actually really strongly correlated out near the wall. So if we said, what am I saying here? So this thing here is, we'll call this V prime, right? That's a disturbance in the Y direction. And then that's going to cause a reaction U prime in the negative direction. Right? So they're correlated and it's negative. So that actually can't go to zero. So this one, we've thought about that one a little bit. That doesn't go away. On the right-hand side, let's see, what are we left with here? This is just some constants, so integrate that. That's going to stick around. What about d squared u bar? Right, this is going to stick around at its average value. And then this d squared u prime, that goes away. We're just taking the second derivative of variability again. So that goes away.